Of course, the challenge is that the moment we become more efficient, that just gets sucked up into us taking on the next big computational challenge. So, we make our TV screens have higher resolution with more colors, right? We're now looking at augmented reality and virtual reality, right? Now, you say, we're looking at neural networks, so AI involving billions of nodes, right? And so the moment we get these efficiencies, it's outweighed by the extent to which we leverage those to push civilization to the next level, right?
Welcome to the Future of Electronics Designed with Cadence podcast, where we explore cutting-edge technology and innovation happening at Cadence. And in every episode, we sit down with experts from across the organization. We talk about everything from the latest advancements in semiconductor design to how Cadence is shaping the future of technology. So you might be curious about technology in general. You might work at Cadence. You might want to work at Cadence. You might want to just know what's happening in the world of technology. And today, I am so excited to welcome the Senior Vice President and General Manager of the System Verification Group, my good friend, Mr. Paul Cunningham. Paul, good to have you here today.
Great to be here, Jeff.
And you look great. You sound great. So tell us about what you do in your role at Cadence.
So I run, like you say, the System Verification Group. So, you can think of Cadence as a pretty large software provider right now. So we've kind of grouped all our products into some broad buckets. So my group, my bucket is everything around and related to verifying the systems and the chips that are out there. So we're about, I think as reported, sort of that kind of 26% of the overall Cadence revenue for my business.
That's a lot of pressure too, but now.
Yeah.
But now that's kind of great. You talked about verification. That is such an important piece of the whole chip design process. And I know we're going to talk today about how artificial intelligence, everybody's talking about AI and ML, machine learning. We could throw around more and more acronyms as we can. So why is it so important? What is it about electronic design and machine learning and artificial intelligence? Why is that such an interest to people today?
Wow. Yeah. So big question. I mean, I think probably what's topical right now is everybody's playing with, Chat GPT, right? It's solving all the world's problems and putting you and I both out of a job probably at some point. But yeah, no, I think, the way I look at it, we're in a very transformational period here as society where we've figured out a way to computationalize intuition, right? To really
I like that.
What we do in the human brain into computer algorithms. So we can build learning, adaptive, intuitive systems. I think, a lot of us probably zoned in on it most heavily when Demis Hassabis, right, who's now of DeepMind, which is now part of Google, came out of nowhere with an AI-based system that beat the world champion at Go. So yeah, this is something that, you haven't programmed, you haven't figured out, okay, deductively, what is the best way to win a game of Go. You just put something in that knows the rules of Go and then has just trained itself. It's just figured out intuitively, just like a human would over playing, billions of games, how to be the best in the world. So yeah, I think it really, the potential to change everything that we do is amazing. Now there are some risks. We all talk about the potential for a Terminator 2 Judgment Day moment, but assuming that doesn't happen, yeah, I think, so AI it influences everything, also in the chip space and in our business. I think probably a lot of people hear about how all of these AI systems now, they use very specialized hardware, specialized computer chips to actually run them. And so, for example, Google have their own special chip called the Tensor, the TPU. NVIDIA make chips, AMD make chips to do this. There's a number of startups. It kind of influences all aspects of life at Cadence and in the world around us, I think.
So where that's great. You bring up some of the key players, and that term you use, computational intuition or something. I love that. That's great. So how is computational? That's a beautiful word.
We invented a word there, I think, maybe.
It sounds. I'm going to look it up right here. I'm going to Google it.
Chat GPT.
What I like is, so you mentioned all the major players or names that household names as far as technology and how we live. How is Cadence interacting or making a difference for each of those companies and the work that your team is doing?
Great question. I think, let's kind of step back a little bit from it, So So all of these chips that are out there in the world, whether it's your Intel CPU in your laptop or in an iPhone or a Samsung phone,
Intel, AMD, right? We have to say, right?
Yeah, all these companies you've heard of, or even little chips that go in your calculator, even these days in your fridge or in your toaster, certainly in your TV. So everyone's heard about these digital computer chips and all kinds of components related to electronics. So somewhere in the back end, somewhere behind the scenes, they all have to get designed and built. And that's a whole industry. It's typically called the kind of semiconductor industry, because these chips, are on a silicon substrate, and they use a semiconductor-based switching technology. So, Cadence is part of that whole ecosystem. We actually build the products, the tools that all the companies making computer chips use to design those chips.
Wow.
So you probably don't hear about us, but anytime you pick up any device with a computer chip in it, you can think of it as, in a way, designed by Cadence.
So Cadence is under the hood in all these major companies and what they do and what they use in their technology.
Exactly. So it is super cool, actually. Now to my specific part of Cadence. So one of the curiosities about these computer chips is it's a really big deal to make one. So you have to spend, tens, hundreds of millions of dollars, and you have to wait a long time. Once you send those blueprints, if you like, for the chip to a factory, to what they call a fab, to build them, you may have to wait 4 to 6 months to get that chip back. So it's a high stakes game, and it takes a long time. So it's it's pretty important to make sure that chip works. So if you're in the business, you really want to have what we, kind of like your flight simulators. So the same thing as flying a big F-18 jet. It's a really big deal. That's an expensive piece of kit. So you don't want to be kind of crashing them all over the places. And of course, you've got human lives at stake as well. So it's a big deal there too. So everyone's familiar with a flight simulator, right? You get in a flight simulator and you can learn a lot. You can try things out and you can train pilots. So in the same thing on the chips, before you actually manufacture these, you want to have all these tools that can help you simulate those chips and make sure that you sure as hell got it right.
Right.
And so that big investment, that big delay, it's going to work when it comes back. And that's that. I sell the tools. My part of the business is all around that.
That brings up the idea of, you talk about the human life is at stake here. So the things that you're doing is so important. You mentioned airplanes. I think something that's even closer to so many of us now is the electric car and automatic driving, self-driving, and even the concept of not even self-driving, but assisted driving, and the brake systems and the alerts. I bought my wife a car, and it has now I know when somebody's on my blind spot and all that. How important is that? And the work that you do could really help save lives.
Yeah, no, another great question. So, I mean, there's actually two sides to what you're saying. So the first, you're talking about, look, we're putting AI right into our everyday lives in the cars. So, we have this driver assist space, right? So the car, if you're not paying attention, the car's going to brake for you automatically rather than allow you to rear end the car in front. It's also even, very common now, right? It will detect if you're moving out of lane, right? And it will shake the steering wheel. So, and of course, we're moving towards ultimately what they call fully autonomous, right? You don't even have to hold the steering wheel and off it goes. So all of that kind of implies in our world as well, right? That designing and simulating these computer chips, it's very human intensive, right? You need a lot of deep expertise and skills. And so there's a mirror of all of that into our world where we're trying to bring driver assist to the process of designing and verifying chips. So we can use AI to help our customers, be much more efficient at making a chip lower cost or lower power consumption or higher performance. Or again, we can use it to help the customer work out, if they find a bug in a chip, where is it, right? What's wrong? How do they fix it? So there's quite a lot of stuff we can do that parallels what you talked about on the cars. And then the other side to that same coin is, all of the electronics that's going in a car, or other safety critical applications, you want to be really, really sure that it's safe, right? So if you've got a electrical control unit for your brake system, you want to make sure it doesn't just crash and you can't brake the car anymore, or not the other way around, right? It doesn't just randomly brake your car when you're going 65 miles an hour on the freeway. So So all of this around what we call the safety and the reliability, that funnels ultimately back into Cadence product. How can we help our customers verify and assure that their chips are actually safe and reliable? And so we have a bunch of technology and a bunch of product that fall exactly into that category.
You mentioned something that made me think back. You said like the simulation, the importance of that, because the cost of making these devices and the masks and going to these foundries and just the fact that they work right. I think about, maybe some of our listeners will remember film cameras. Hopefully many do, where we take, and that's kind of like you said, sending it off to the foundry is like we'd send the roll of film off to the lab, and then there was the 1 hour photo. But even before that, we'd mail it away and it would be weeks, and we'd get it back. We go, is the picture good? Then digital photography came out, and it's instantaneous. I get a response. And I think about, that's almost simulation is. I take a picture and I have some feedback to know how it's working, and the importance of that around, the cost of developing a roll of film was not much compared to the cost of making a chip. And there's some analogies there. And you have all sorts of platforms that do that.
I haven't heard that analogy before, Jeff. I think it's a really great one. Yeah, the point that, in a way that you could think of the computer screen, the little LCD screen on the back of your digital camera, that's simulating, right? It's that's showing you what you're going to take a picture of, what you're going to kind of print. So yeah, if you can see that and you do that, you can make sure you got the shot right and it's framed right and everything before you click the snap button. So it's a great analogy, and that's exactly like, it's just that fact that, imagine if every time you click the button, it's going to cost you tens or hundreds of millions of dollars. So you really want to make sure you got it right.
You're not pressing that button.
Yeah.
And what's great is that you come from such a unique background. So you had your PhD, I'd say, at Hogwarts, which was at Cambridge University. Maybe you could tell us about that, and how you got to Cadence, doing a whole different. Your focus came from actually the kind of the architecture, laying out of the chip, and now you've taken that computational expertise, if you will, and moved it over to the verification space. So maybe you could walk us through your background of your studies, what you did, how you started companies, and you still look, to me, you still look like you're 20 years old. So you have such a great youth and energy about you, and you've done so much. So maybe you could walk us through some of your history.
Sure. Yeah, no, gladly. I don't feel as young as I used to be. And I keep my hair short. When I do go to the hairdresser and they're cutting it, it definitely comes down pretty white right now. So yeah. Hey, when you mentioned the Hogwarts thing, that actually made me smile. So yeah, Cambridge University, for those the listeners that haven't been there, I mean, you're talking a university that's 700 years old, right? So it's just in a completely different league to colleges in the US.
Well, they finally painted last year, I understand. They repainted a few.
Yeah, well, so I mean, a lot of it is kind of obviously preserved, right? It's heritage. And
so, what was your course of study? What was your PhD in? And then you started a company. Tell us about that. I think that's very interesting.
So I studied computer science. So I did both master's and PhD in Cambridge. And yeah, right from a young age, I mean, I've always just loved computer algorithms. So I remember that sort of very first time, we had, it was like I think it was an Amstrad PC, and it had BASIC, and I started realizing, that you could write a computer program that would print out the multiplication table, 2 times 3 is this, 4 times 3 is, but yeah. So it was really amazing for me, and I think that from that moment I was hooked. It's like a kind of the pure manifestation of puzzle solving, and it's that kind of wonder you get that a computer can solve the problem so much better than you can. It's so much more efficient. So it feels like you've got this sort of unlimited power at your fingertips. I mean, literally the keyboard fingertips. So so I studied computer science, and that definitely gives you a much more formal grounding. So they really do make a science out of programming, and so that was it was wonderful for me. And of course, 4 years wasn't enough, so I definitely wanted to stay on to do the PhD. And there's another, maybe we get to it. I also spent way too much time in sport and rowing. In undergraduate. So then I was also like, well, hang on a minute. I've just graduated, but I didn't have any fun. So I need to kind of, stick around a bit longer. So the PhD is where I started to get more in the direction of Cadence. So I got into these, software programs that are for helping you design and verify computer chips. So that's kind of where my PhD was. And it was actually in more of a niche area called asynchronous chip design.
Mm-hmm.
So, most of the chips that are out there in the world today, you often hear about a clock or a frequency. So you say, oh, my Intel PC runs at 4 gigahertz or 3 gigahertz.
Right.
So that number, so 3 gigahertz really means that there's 3 billion operations per second. So everything that the chip does is synchronized, right? It happens to a global drumbeat, right? Called the clock.
Right. Very
literally
well
a
said.
signal that goes across the whole chip. And every time that signal changes from a 0 to a 1, it counts as beating the drum. And then all the operations, everything on the chip is coordinated to that global drumbeat. And it's a very powerful technique. It's enabled us to build tools and automation and methodologies to deliver, the world that we see today.
Right.
But there was kind of a small group of people that said, well, no, you don't actually have to have a global conductor. You can be more like a kind of swarm of bees or ants, right? So stuff can just get done.
A little more entropy. Yes.
It's all locally coordinated. It's all locally synchronized, right?
Mm-hmm.
And so and they believed that there were certain potential benefits from ditching this global synchronization. So they called it asynchronous, the as in not synchronous. I kind of got into that area, and I was young. I believed what I was being told. I sincerely believed the benefits. Like they said, it allowed you to make more secure chips. It allowed you to make lower power chips. Obviously that didn't play out. So that the story goes that I actually came out to the US to intern at Sun Microsystems.
Okay.
So this was at the time when Sun was the .com, and
absolutely
most of the campuses in Silicon Valley were Sun Microsystems campuses.
Yep.
And so I was interning there. They had a research labs, and they had a small group that were looking at asynchronous chip design. And at the end of that internship, the person I was working for, offered me a job. He was a wonderful person. Ivan Sutherland. I have huge respect for him. And I kind of blurted out something fairly incoherent about startups and Bill Gates, and it was the .com era, and I think subconsciously hoping that he would talk me out of it and say, don't be silly, come work at Sun. It's an amazing company. I'll show you the ropes. But he actually said the exact opposite. The moment I started talking about starting a company, he doubled down on it. He said, "Oh, don't come work for me. If you've got the itch to do that, you should go do that." And the more you don't do that, if you go and get a job in a big company, it will just give you more and more reasons to not do it.
Right.
So it was, and then he introduced me to the idea of angel investment, and he said, so I was like, okay, I'm going to go and do my own startup, and we're going to make asynchronous design tools. Off I went, and I started the company. I found that my buddy, the smartest person I knew, and convinced him to come and start it with me. But we were both pretty much straight out of PhD, so we really, looking back, didn't know anything. And of course, so we got some angel money, and we got going, and then I got out there and started talking to real companies and real businesses that were in the business of making chips, and quite quickly realized that asynchronous design wasn't all it was cracked up to be, and that actually there were very good reasons for people doing synchronous chips. So I think we didn't call it anything back then, but we essentially had to pivot. So the funny story with this is that all of that experience made us realize really what it was that was great about synchronous design. But there were a few limitations. We could do a little bit. We could make the clocking in synchronous design a little bit better. So we actually turned into what was called a clock tree synthesis company. So we got into the business of building clock trees for synchronous chips. So it was more like asynchronous inspired synchronous design.
Right.
So we actually, we turned to the dark side, I think, in the terms of my academic community. But that worked much better. That actually really, really was quite successful. And so we chipped along and grew to about 50 people. And then very fortunately, the planets aligned for us to become part of Cadence. So that was just over a decade ago, around 2011.
But it's great that your exploration and your curiosity and your background and your drive, which is still there, got you to Cadence to make a huge difference in the place and route area of our tool set. And then from there, you maybe you could share a little bit about how you then transitioned and look at how the opportunities opened up. You came in, your company was acquired, you built something out of your dream, and you've been able to take that dream and continue to grow it in the context of working through Cadence. Maybe share some of that.
Yeah, absolutely. And probably a good moment to a little kind of thumbs up to Cadence, the business. I am still here, right? I didn't leave Cadence. I didn't go do another startup. And that joy I have for computer algorithms, right? And just solving complex puzzles computationally. What you realize if you join Cadence is that the space we're in is littered with amazing computational problems. So I kind of joined in, like you say, our startup's technology became the clocking technology in Cadence's products. And even still to this day, that part of the Cadence solution, the team, the what we call the R&D team that write that software component in our solution are based out of Cambridge in the UK. But pretty much every single product in Cadence's portfolio, so we got whatever $3.5 billion worth of product. Every single one of them has a super exciting computational problem it's trying to solve. So, if you like algorithms, you like computer science, it's like being a kid in a candy store joining Cadence. And it's just wonderful. So I think that's why I'm here, because now all of a sudden, what I love and enjoy, I've just got a massive range of opportunities and we encourage that. So like you say, I started doing that clocking, but actually within 3 years, I'd moved on and I was working a lot more on placement and routing. And then it moved on and I actually moved into what we call logic synthesis and logical equivalence checking, design for test, high-level synthesis. These are all kind of like buzzwords in there, but they essentially think of them as just different products solving different kinds of algorithms to help companies make better chips faster and with less effort. And now the last 5 years, I've been in the verification part of Cadence. So that ability to just kind of move within the organization, I mean, it's wonderful. And I'm still the kid, just the gray-haired kid in the candy store.
And for people that are looking at Cadence to say, is this a good place for them to work? Do you still see those kinds of opportunities there for them to contribute to your team or other parts of Cadence, coming in with a curiosity and excitement? And now with everything going on in artificial intelligence, that there's just so many opportunities here to participate and contribute.
Absolutely. Yeah. And our CEO really refers to Cadence as a computational software company. That's what we do. And we think we've got some of the world's best computational software engineers. And so definitely. And we continue to see people moving, between product lines in Cadence. I would say don't move too quick. If you change focus every 6 months or every year, you haven't got a chance to master anything. So I do feel, if you pick something, you should spend a good 3 to 5 years at it. But to spend 30 years on the same algorithm or the same product line, no, that works. Can work very well for some people, but for other people, they like to change. And definitely, I see that continue to happen at Cadence, and it's kind of one of the joys of being here.
Absolutely. And in addition to all that we're doing with AI and ML and making things more efficient, we're also using some of that technology to look at how do we reduce power and also environmental sustainability. There's a lot of that going on, not just as talk, but we see it happening, actual actions. Can you share some of the things that you're participating in, or what Cadence is doing in the areas of power, lower power, sustainability, environmental focus?
Yeah, I mean, totally. It's a great point, Jeff. The industry, which cannot exist without companies like Cadence delivering all of these tools. We've just delivered orders of magnitude over the last 20, 30 years, improvements in power efficiency, just driving as we've driven the underlying devices, this thing called the transistor and the wires, to be smaller and smaller. We've had more and more advanced and we have phenomenal complexity now in our software to allow, we're talking hundreds of electrons, literally just hundreds of electrons defining the difference between a 1 and a 0 or an on and an off. I mean, it's
not many. That's not many.
No, it's just unbelievable. So the complexity that goes, and when we're printing shapes, we're printing features that are, down to like 5 or 7 nanometers. So it's unbelievably advanced. So but by doing that, right, we've achieved phenomenal improvements in the power efficiency of what we can do. Now, of course, the challenge is that the moment we become more efficient, that just gets sucked up into us taking on the next big computational challenge. So, we make our TV screens have higher resolution with more colors, right? We're now looking at augmented reality and virtual reality, right? Now, you say we're looking at neural networks, so AI involving billions of nodes, right? And so the moment we get these efficiencies, it's outweighed by the extent to which we leverage those to push civilization to the next level, right? To deliver new technology, new experiences. So it's never enough. And now, it's amazing. We can make, a new release of our software, which will squeeze, make a chip 10% more power efficient or 20% more efficient. And that adds up. That counts, right? If you're talking added up at scale across, terawatts worth of capacity, right? It's really significant. So yeah, I think we have we're really playing, and we continue to have a huge duty and responsibility to make the world's electronics as power efficient as possible. Yeah. And I think, we'll see that, right, over time. You hear stats like crypto, they talked a lot about just what percentage of the world's power consumption was going in crypto mining.
Exactly. Right.
And now people are starting to add up, how much power consumption is going in AI, right? AI computation. So, these are some of the biggest consumers. I think I heard, the worldwide data center power actually is as much as the airline industry, the worldwide airline industry. It gives you a sense of just how significant it is.
Well, it really is amazing the amount of data that has to be processed, or when we do even a simple Google search, just how many machines are going in the background, or et cetera. And if we look at the efficiency and using AI and ML, we come back to that same question again. Are we going to get so automated? Is technology and the work that we're doing at Cadence, is it going to get so easy that we could literally be replaced? Right? You mentioned earlier, where our not just our term papers are written by a machine, but our jokes, our jobs themselves. Are we going to eliminate the need for you and me over time? What do you tell your kids when they say, "Dad, I want to go into technology, but you've done such a good job that everything's automated. There's nothing left"?
I don't believe so. But I can't profess to be an expert on this. This is really uncharted territory. But I think we will just evolve. So our contribution will shift to be at a different level of abstraction or in a different way. So the moment that we have this automation, we then use that automation to push the boundaries further.
Right,
so
for the next problem.
Yeah. So
right.
I think, I believe that's what's going to happen. The notion that there will be, we'll reach this singularity point where AI, we have the Skynet scenario, right, where the machines take over the human. Yeah, I don't know. I don't personally think that there's any risk of that. No,
that's right. And if we do, somebody's going to write. They say we get paid for every bug that we find, and then people are just putting the bugs in the code to get paid. We'll figure something out, and we'll manage our existences. But if we look forward, so if I asked you, what's the most exciting challenge that you have on your plate in this coming year that you'd like to attack and address and really make progress on, what would you share as we wrap up for today?
Oh yeah, great question. So I think ultimately for this year at least, right, the big challenge is making sure that we continue to meet all of our customers' needs, right? So there's a lot of change, a lot of going on in the global economic situation, geopolitical situation. So really being there for everybody that we're supporting, and being there for the people at Cadence, right, and the workforce at Cadence. So I think that really, and staying strong, staying true to our computational software vision, right? So that's actually really in the forefront of my mind now, because we've got so much that we know we need to do and we can do, right? As I talked about, continuing to enable our customers to shrink these transistors, right, and shrink the wires, and continue to bring more and more driver assist to our products and solutions with AI. So kind of our roadmaps are really clear. We're bursting with vision and we're bursting with technology ideas. But, so we just need to make sure that we can really deliver that with quality and making sure that, we don't burn out all of our employees, right? And take care of the planet, take care of our people, take care of our shareholders. So I think all of that, right? Just really being a great company and a great place to work. That's actually what's most on my mind at this point.
I love that, Paul. And I want to go back to that statement you shared at the beginning. Was it computationalized intuition? Was that the right phrase?
Yeah, that's right. Yes.
I love that. And the work that you're doing in the team, I think it's tremendous, and it's allowing people to get chips out on time, to be smarter, to be more efficient, to be more cost effective, to handle all issues before you go to manufacturing. And again, any last words you want to share today with our listeners?
I'm going to say glad to be here. So recently was privileged to listen to a talk by John Fowley, a former Blue Angels pilot with the US Navy. And if you're interested to find why I'm glad to be here, go check out John Fowley.
Paul, that was tremendous. Thanks for taking the time with us today to talk about the future of electronics designed with Cadence, specifically focusing on artificial intelligence. We hope you all enjoyed listening and learned something new about how Cadence is applying artificial intelligence to verifying chips, as well as how we're managing the environment and concerns about power and sustainability. And we want to encourage you to tune into our future episodes where we explore other ways of how Cadence is shaping the future of technology. Follow us on social media, and we'll look forward to seeing you all again soon. Thanks very much.
Thanks, Jeff.